We're getting into partial fraction decomposition. It's actually a pre-calc skill, but very often it's a skipped pre-calc skill. So I'm just going to give you a little bit of background on that and then take you through some applications for integration. All right, so the idea is that if you have a fraction, it could be the sum or difference of two other fractions. All right, and the idea there is that those two fractions that are added together could be simpler, as in more integrable, than the one that you're presented with. All right, so let's say, for example, I have some fraction that's in the form of a over ax plus b. All right, so it's a constant over some linear relation, or a linear expression. I don't want to overuse the term. All right, my fraction bar looked a little wonky there. This could very easily be, assuming a common denominator, the sum of two fractions, each having differing numerators. All right, same denominator, but different numerators. Okay, and if that's the case, it really would just be a matter of determining what those values are. Now, there's one way to do it. One way, you may not like it, but that way could be trial and error. All right, you just figure out what two values would make sense in order to get you the one that you're looking for, and there you go. If this, for example, was equal to 5, then you could say 2 and 3, you could say 4 and 1, you could say negative 2. Actually, let me put it as a negative 2 and 7. You know, all these different possibilities. Infinitely many of them. All right, so we don't want to go down that road. We want to have a technique that we're going to be able to use repeatedly to help us determine these values. All right, and so what we do is we solve. And the way to handle that, in most cases, is going to be to clear out your denominators. So multiply everything by whatever your denominators are, ax plus b. In which case you'd have a times ax plus b over ax plus b equals, I'm just going to do a copy paste here and just throw some subscripts in. And then you'll be able to cancel across the board and see that it's really just a equal to the sum of a1 and a2. If we have a quadratic on the bottom, let's say it's in the form of ax squared plus bx plus c, and you have some linear expression on the top. So I'll say a1 x plus, actually just ax plus b. Now, we could have some factors, right? We could have some factors of the ax squared plus bx plus c. If that's the case, then we might be in some pretty good shape, right? So what I'll do is I'll just say x minus r1 as a factor of in one instance, and then x minus r2, you know, r for the roots. But if we're assuming it's quadratic and it's factorable, then it would be in the form of x minus some root and x minus some other root. Actually, even if it's not factorable, it would still play out that way. It's just, we're going to make the assumption that it's clean. You know, and to account for the a, you might even say it's x minus some fractional root. All right. Now, in order to solve this, you know, so again, we're assuming the roots, the factors, are x minus r1, x minus r2. Right. To solve this, we'd have to make some kind of an assumption as to what the numerator is, or numerators are. ultimately, I want to, one, clear out the denominators. If I do that, what I'm going to, let me just copy paste first because it's going to become messy. I'm going to try to take this. All right, so far so good. And then I'm going to get rid of this and move these up. What we would be doing here would be multiplying by the quadratic. So in effect, I'm just going to multiply everything by the x minus r1, x minus r2. And you're like, but you didn't put anything in for the numerators. Yeah, there's a reason for that. Kind of showing where this is going. Although, what I'll do here is draw the parentheses, shrink it down, and just kind of slide it in there somewhere. Move that over some. We'll just kind of chuck that in over there. Okay, so on the left-hand side, I would have an ax plus b. On the right-hand side, I'd have a cancellation of the x minus r1. And that would leave me with, if this were just a 1, it would leave me with the x minus r2. If this were just a 1, when I multiply through with the product of factors, I would be left with just an x minus r1. All right, but we can't make that assumption. So what we do, especially since all we need is something linear, and we know we'll be introducing an x into the numerator, is we just state that we know that there's going to be some constant value here that we'll call a1 and some constant value here that we'll call a2, in which case we would have a1 multiplied by x minus r2 plus a2 multiplied by x minus r1. All right, so basically your denominators are canceling, and whatever remains is going to get multiplied by the numerator, which is going to be some constant. If I had an x in there, then when I multiplied it by a term that has an x in it, it would create a power of 2. But I'm saying here that I don't have a power of 2, nor do I want one, so that would be the end of that. All right? So the next step in the process here would be to clean things up. I'd have a1x minus a1r2 plus a2x minus a2r1. And that's equal to ax plus b. So to solve here, anything that's got an x can be set equal to one another, or equal. So ax is really equal to a1x plus a2x, which leads us to conclude that a has to be the sum of a1 and a2. Those two coefficients have to combine to give us the coefficient of a. B, on the other hand, has to be the sum of anything that did not contain an x. So b is going to be equal to negative a1 r2 minus a2 r1. All right. So yeah, we don't have all the answers here. We don't have all the information because we're working in general terms. But I have a way to solve for a missing set of coefficients or constant numerators, provided I know what the R1 and R2 values are. All right? And, you know, I got to be given a capital A and capital B, but if I have that information, I have everything I need in order to solve this problem. All right? So that brings us to this first example here, which follows that same idea. So we have 4x plus 41. We have, the bottom here is factorable to x plus 5x minus 2. So I'm going to assume that there's some constant numerator over x plus 5 and some other constant numerator over x minus 2. So then what we do, just like we did above, is we multiply everything by x plus 5x minus 2. On the left-hand side, you get a clean cancellation so that it's just 4x plus 41. On the right-hand side, the x plus 5 will cancel with the x plus 5, leaving me with just an x minus 2 multiplied by a1. So a1 times x minus 2. When I multiply that by the a2 over x minus 1, everything gets reversed. Right? So the x minus 2's will cancel, leaving me with just the x plus 5 multiplied by the a plus 2. A plus 2. A times a. I'll get it right eventually. A sub 2. Alright, so I got an x plus 5 here. So 4x plus 41 is equal to a1x minus 2a1 plus a2x plus 5a2. Anything that's got an x can be equated. So 4x is equal to a1x plus a2x, which tells me that 4 is going to be the sum of a1 and a2. All right, so telling me even more specifically that if I needed to guess and check, at least I know what neighborhood to be in. Maybe they're both 2s, the a1 and a2. Maybe 3 and 1. Maybe it's 5 and negative 1. Who knows? All right, it's the other relation that's going to narrow things down for us. So 41 is going to be negative 2a1 plus 5a2. And so now we have a system of equations. All right, so I can pair them up. And use some elimination. So I'll multiply the first equation by 2. So 2a1, I lost my subscriptive 1 here, and here. 2a1 plus 2a2 equals 8. Add that to this bad boy right here. And you're going to get 7a2 is 49, which means a2 is equal to 7. All right, so we have that. So we're in good shape there. So now it's just a matter of figuring out what the a1 is. Well, I know that a1 plus a2 has to be equal to 4. So a1 must be a negative 3, because negative 3 plus 7 will give you a 4. So now we can start the problem. Look at that. So all of that was to get this into a form that's integrable. So instead of writing 4x plus 41 over that quadratic, I'm going to write negative 3 over x plus 5 plus 7 over x minus 2 dx. All right, so this looks like a natural log. All right, so ln of x plus 5, well, if I differentiated that, that would be 1 over x plus 5. So let me just slap on a negative 3, and we'll have equivalence. ln of x minus 2, if I differentiated that, would be 1 over x minus 2. So let me slap on a positive 7 for equivalence, put a plus c at the end, and you have it. All right, so this is all about just taking something that's complicated and making it more manageable.